Okay, dann willkommen in der heutigen CMOS-MEMS-Vorlesung. Wir schließen das Kapitel Magnetic Sensors. Sorry. Yes, welcome. Yeah, willkommen. Yeah, so it's all the same, you know. It's all Anglo-Saxon. Yeah, I try to avoid the French words. No, I start using the French words again, and then German becomes English. Yes. So welcome, and we'll continue to finish this chapter on magnetic sensors, and then we'll be able to start with the mechanical sensors, mostly based on piezoresistors, stress sensors. And so I've shown you now quite a few examples of magnetic sensors based on silicon technology, in particular CMOS. And here is now one that is also based partly on silicon technology, but not on CMOS. It is an option to integrate the sensor into CMOS technology. Whether this is meaningful is another question. But anyway, here is the principle. We have talked about resonance sensors yesterday, and this is another example of a resonance sensor that was developed by Simon Brucker in my group in the frame of a PhD thesis funded by a Graduiertenkolleg. Well, he found that these sensors here that we discussed here have some disadvantages, and he really wanted to go beyond those disadvantages. So after quite a time of pondering and creating proposals and rejecting them for various reasons, he turned up with an interesting device that is shown here, where you see a central resonator here. So this is imagine this to be a mass suspended on a spring, able to vibrate horizontally between its two clamps. And then this oscillating mass also bears part of a magnetic concentrator, which you see here from left to right. This is a magnetizable material that kind of draws in the magnetic fields of an external magnetic field, concentrates them, and channels them through its material, through the second piece that is mounted on this oscillator, and then back into the third piece, which is symmetrically placed on the right, and then the magnetic field lines escape again. And so you can imagine that this central piece, of course, when deflected into positive directions, into the positive direction, experiences a mechanical force that restores its original position to the middle. Yeah, so this is indicated by the blue arrow, and this mechanical force is proportional to the deflection in the positive x direction, delta x, from the equilibrium position with a mechanical spring constant k mech. And then, if there is, if there was nothing else, we would obtain a mechanical resonance frequency that you would see down here in the form of square root of k mech, the spring constant divided by the mass, the effective mass of this object. Should we count a little bit of the spring mass also? So an effective mass, the square root thereof, and this divided by 2 pi. That's the resonance frequency of this mechanical oscillator alone. But if there is a magnetic field present, then you can imagine, and I'm drawing this schematically. So let's say here comes a field, here is a south pole, and here is a north pole, and then here is another south pole, another north pole, another south pole, another north pole. So there is an attractive force between these north-south pole pairs in the center. And if the resonator is in the middle, of course, if the gaps are the same, the forces going towards the left and the right will be the same. However, if the resonator is displaced, one of the gaps is going to be smaller, and then the force between, let's say, if there is delta x proportional, and a positive, then this gap becomes smaller, and then the attractive force of this pole pair exceeds the one on the opposite side. So actually displacing the mass, the central piece of the concentrator, increases a force that goes to the right, to the same direction as the deflection. So we model this in the linear response as a magnetic force that is proportional to delta x with a spring constant that is negative. Actually, you can imagine that you deflect the whole thing strongly towards the right concentrated piece, and then the two pieces will stick together. The energy will be lower than in the middle. So this kind of explains this energy landscape, which is parabolic for the mechanical and then parabolic for the magnetic force, and both effects contribute to the overall spring constant, and that's shown here by the difference, or by the sum of this positive and this negative spring constant. And the spring constant of this magnetic effect depends on the external field, of course. If there is no external field, there will be no such effect. However, it is also clear that if the magnetic field comes from the other side, the effect will be the same. It will be insensitive to the direction of the magnetic field. The only thing that will change is the polarity of the poles. S will be replaced by N and vice versa, and the forces are still attractive, of course. So is it a good thing to have a magnetic field sensor whose response depends on B square, on the absolute value of B? Let's see what creativity goes into the design of a sensor to overcome such possibilities or such drawbacks. So here is a more realistic outline of the structure. You have these fixed magnetic concentrator sections out here. We'll have to see where they are fixed. There is a mobile section. This mobile section is guided in a uniaxial motion without rotation, torsion, and so on by flexural springs, blades that are produced by reactive ion etching, and that can then be dominantly or most easily deflected in this flexural mode, enabling this, for example, one-dimensional motion. And then this central piece is equipped with fingers, electrostatic fingers that can interact with electrostatic fingers from external fixed electrodes. So these electrodes move with respect to each other, and they can be applied to either exert an electrostatic force on the central piece by applying an external voltage to deflect it or to put it into resonance, actually. And then others can be used to measure the amplitude of that resonant motion. So this is the principle. This central resonator is excited into resonance, and its resonance frequency is going to depend on the magnetic field, and measuring that amplitude makes it possible to determine the resonance frequency of the resonator, and that makes it possible to indirectly determine at least the absolute value of the magnetic field, maybe more. So this is a not so microscopic device. It measures 5 millimeter in length from here to here. I mean, this was a prototype that he realized. Actually, Simon realized a microscopic prototype first to demonstrate that this principle really worked with microscopic pieces and the resonator that did not resonate very fast. And then we saw, okay, wonderful. He could also try all kinds of tuning mechanisms to show how to increase the response. And then he went into a micro machine version, which I show here. And so a critical part of this structure is this magnetic concentrator material. We used so-called MET glass, a product from Asahi company in Japan. There was a guy called Hasegawa who knew how to produce these metals, these magnetizable materials. And the important part is that they have extremely low coercivity. So this is, the coercivity is basically the field that you need to apply to invert or to get the remnant magnetization to zero. this material has very low remnant magnetization. It is easily magnetized, and when there is no external field anymore, the magnetization goes back to essentially zero. And how does one do that? By making an amorphous material, an amorphous metal. So you will think of metals having crystalline structure, or at least polycrystalline structure. But if you cool down a melt rapidly enough, the atoms don't even have the time to think about reorganization into a crystal. And this can be supported by making alloys which hinder the motion, the migration of atoms. And McGrath is one such example. So these ribbons are spin cooled over a cold wheel, and high speed and roll, and then we get a section of that roll. And the material, of course, is rather thin because the heat must be extracted very rapidly from the melt, so you don't have a large thermal distance available to make that cooling process rapidly. And that's why this foil is rather thin, 18 micrometers. But if you would like to have thicker pieces of that material, just glue layers of that material on top of each other. Professor Wallrabe has done that extensively to produce transformers and actuators and so on. When she saw our results with that miraculous material from Japan. And so how to realize a micromachine version? So here is an SOI wafer, silicon oxide insulator, silicon insulator, silicon, SOI, silicon on insulator. And then this is equipped with some contacts, so the top material can be put to a potential, various contacts wherever they will be needed in the future. And then some trenches are etched here to realize, let's say, the basic mechanical structure as you see here. To carve it out of the surrounding silicon material. Then these trenches are filled with photoresist. Aluminum is protected with photoresist. Then an epoxy resin is spun on top, and the met glass is glued on that epoxy. Then the met glass can be etched with aqua regia, in German Königswasser. That's one of the few etchants that is able to etch even gold. So it's very effective. You have to be careful with it. It's highly aggressive. And then even met glass can be etched with that. And then the epoxy needs to be removed by oxygen plasma. This is an organic compound. So oxygen plasma does the job of breaking up these bonds and removing the material down to the no longer organic materials, namely the silicon here and the contacts. And then etching can be done from the back. So there is etching with deep reactive ion etching, then some reactive ion etching to remove the oxide, and then some removal of the green material. Well, it shows better on the screen there than on my computer. So these sacrificial fillers here in green, this material is also solved by a solvent. And then we have a structure that still is connected by one piece of met glass spanning the whole width. And then these cuts need to be performed, which you see here. And that is done by laser micromachining. And those cuts need to be small. So it's 18 micrometer thick material, and we would like to have a cut that is not 100 micrometer, like a few micrometers. The smaller, the better. The stronger the effect will be. And so we at this at Karlsruhe at the facility that they have their laser machining facility. Yeah, so this is a top view structure. You see also here cutting with the laser, produces a gap of a few micrometers. This is 10 micrometer here, so maybe 5. Simon had several thicknesses. You see also that laser cutting causes all kinds of secondary deposition, so it's not a perfect machining technology. But anyway, here you see cut 1 and cut 2, the central piece of the concentrator, and the outer concentrators adjacent to the central piece. You also see the interdigitated electrodes, connected to some individual pads on which you can bond wires to get some voltage out or some signal, voltage in or some signal out. If I zoom in into that, you also see that the placement of these electrode pairs is asymmetric, so that when we apply a voltage between the inner part and the so this resonant part, which is seen here, maybe now you understand, and here this fixed electrode set, if I apply voltage, there will be an attractive force towards to even close that thinner gap more thinly. And so this is the structure. Let's go back to a decent size. Here we go. And now how to measure that this, how to prove that this sensor actually works as a magnetic sensor. So we placed it in the Helmholtz coil that we have at our disposal in a magnetic field, external magnetic field, and then we can vary this field. Now the Helmholtz coils are not small coils, but they are rather large coils with a small distance in order to create a very homogeneous field in the center. There are dimensions that make this possible to have as homogeneous a field as possible by compensating nonlinearities by geometric design. And then, so what will one observe? Okay, well, at let's say 0 micro Tesla external field, and we're talking about micro Tesla here. We have a resonance frequency of 2,500 hertz. And then when the magnetic field is increased, let's say to positive values, the resonance frequency decreases. And when the magnetic field goes in the other way to negative values, well, the resonance frequency also decreases, as expected, insensitive to the direction. Nevertheless, interestingly, you see that it doesn't decrease the same way in both directions. So, similar surprise. Is the Helmholtz field the only field that you have in your lab? There is the Earth magnetic field. So actually, the fact that this point here at minus 400, let's say here, is at another value than at this 400 here, or here this measurement point at 425, those 2 points have a delta F resonance, is due to the fact that for positive and negative Helmholtz coil field values, there is the same field added on one side and added to the negative number on the other side, which shifts the whole curve to one direction. And that said, okay, lucky you. You notice that we can measure much smaller fields. It's interesting to know that you can measure fields with by having a delta F. So this would be some resonance frequency change, delta F resonance frequency. Let's say really the main thing, but it's quadratic, so it's totally unhandy for small fields, and it's direction insensitive. But thanks to the magnetic field of the Earth, we saw that there is a split. And if the Earth's magnetic field was pointing in the other direction, we would have to split in the other direction. So if you rotate your Helmholtz coil in the lab and you make a measurement, you will see that the delta F goes up, and then it goes to 0 again, and it goes to negative, and it goes to 0 again as you complete the full circle. So you have to make a compass. It's a big compass. A Helmholtz coil plus a microsensor. So at least, this was proof that you can measure the Earth's magnetic field. A compass, which is hard with a semiconductor sensor based on silicon. 20, 25 or so micro Tesla is small, but it produces an effect here. And then, well, also, of course, this device was characterized in vacuum as well as atmospheric pressure, and it resonates much better, with much less excitation or a much sharper resonance frequency in vacuum than in air, where it is broadly damped by frictional effects in air, by squeeze film damping, by present in mechanically moving microstructures in air, and so it is definitely so that under vacuum, the sensor has a chance to enable better resolution of delta F, and the better resolution of the change of the resonance frequency by the magnetic field, and therefore also better resolution of this delta F. So let's think about the Helmholtz field to be an auxiliary field to measure this other field that was, I would say, a disturbing factor in the first measurement, the initial measurement, but which now becomes the main field to be measured. Therefore, the Helmholtz coil is actually only an auxiliary field. So let's call it auxiliary to turn the idea away that this has to be a big magnet. So the delta F is F resonant at B plus B aux minus F resonance at B minus B aux. And if the resonance function is a quadratic function, as it seems to be, must be, to first order, then you can write it as such, and the other one as such, and then you simplify, and at the end you have delta resonance is equal to 4 times this arbitrary constant that translates or represents this parabolic curvature of our curves, and then B and times B aux. So we have a response that is proportional to the external field. That's exactly what we want of a sensor. And it's proportional to a parameter that we can even set technically by applying an auxiliary field. If we don't do that, then we have nothing. If we make it strong, then we have something strong. And the sensitivity, the absolute sensitivity would then be the change of the resonance frequency per magnetic field, which is obviously this number. So how to produce a sensor with integrated coil to have an auxiliary field generated in situ of the sensor. That's the next challenge of Simon, and he did this by taking his original structure and adding some planar coils on the surface of the chip, as you see here, with 2 pads that can be bonded, to which a current can be sent through to generate a magnetic field. Same on the other side, where the auxiliary magnetic field will point now downward, the one on the left outward, and then this field is sucked into the concentrator and out of the concentrator into the other coil. So this is the way to make an integrated Helmholtz coil, a flat 2D Helmholtz coil, which does no longer serve the purpose of making some field homogeneous, but it generates an auxiliary field, and that's all we want. And now this structure, you see it on the right with its auxiliary coils. It's impressive size, 7 millimeters by 3 millimeters. I mean, is that still micro? Well, some features are micro, and the gaps are definitely micro. The electrodes are definitely micro also. And so if we look at this structure now, and measure the delta F that is enabled by operating this with the auxiliary field generated in the chip by just sending the current through those planar coils, you see that the response, the delta F, depends on the rotation of that little chip. And now we have a little compass that is definitely smaller than a compass needle in its classical housing. The resolution was good enough to enable the Earth magnetic field to be determined as 17.4 microtesla. Now in Germany, it is supposed to be 20.85 microtesla. Then also you have to think about the fact that the Earth magnetic field goes in at a slope. So you're measuring the horizontal component. Actually, Simon could have tilted his chip also to determine the real direction of the Earth's magnetic field, maximizing this amplitude swing. But it's not unreasonable. And the Earth's magnetic field is known to vary depending on the geology, and how much iron you have nearby in the ground. And, you know, mountains are maybe a reason for the presence of other geological situations than what is in this southern Germany value, taken from some source. Yeah. And with sinusoidal curves of this shape, you can, of course, make measurements with an angular resolution, which in this case, Simon estimated to be 5%. Okay, we didn't know about error handling then. I know much better now with Bayesian methods and so on. We could really get a firm number written down here if we wanted. So this is, I think, the last slide of this chapter on magnetic sensors. And well, it showed you a topic that I like a lot because it has quite a bit of physics in it, a lot of technology and interesting secondary effects that disturb the people who want to sell products. And yeah, you have to really squeeze the maximum out of the sensors. Good ideas have been generated by that. Yeah, now next I will move to stress sensors or mechanical sensors, I could just call that chapter as well, which, yeah, is an interesting topic also. I like it a lot. So this is first about piezo resistance and piezoresistive sensors. Yes. God, I don't have them here. I need to call my secretary. Of course I have them, but they're in the lab. Yeah, in the lab in my office. So secretary, contact, Miss. No, not this number. This one. Ja, hallo Manuela. Du wirst jetzt gerade im Zoom-Recording aufgenommen von der Vorlesung. Ich brauche nämlich deine Hilfe. Ich habe auf meinem Besprechungstisch einen Karton mit Skripten. Ja, da sollte draufstehen Chapter 4 Stress Sensors. Ich wäre dir dankbar, wenn du den herüberbringst. Und herüber ist wo? Das ist im Gebäude 51, glaube ich, heißt das hier. Also das ist das, wo früher der Professor Becker saß oder die Hanna Bast, ja, die sitzt da. Genau. Und jetzt, wenn du da bei der Poststelle, also auf der Seite hineingehst, gehst du fast ans Ende des Gebäudes und dort die Stiege hinauf bis ins oberste Geschoss. Ja, da gibt es den Raum 0, wie auch immer, 50, 03, 26. Dort bin ich drin mit studieren. Ja. Ja, Stress Sensors. Ja, okay. Vielen Dank. Ja, okay, danke. It's wonderful second. My brain, my second brain, or my legs, however you would like it. Yes, I'm glad. This is so easy. I'll keep the phone here to see if she calls me back. So, first topic will be about piezoresistance in general and piezoresistive sensors. Then I'll present some sensor systems for pressure, force, moment, and then a particular application, microelectronic packaging testing. This is a project which we had with Intel. They wanted to learn about their packaging with stress sensors, you know, how strained is the material, and if you can design stress sensors wherever you want on some silicon chip, then you can extract that information. So I jokingly always say we were inside Intel. Yeah, it's the other way around. Yeah, people usually have Intel inside. Yeah. So it was interesting to have this project with them, and then at the end I would like to talk a bit more in detail about membrane pressure sensors, because that's one of the strong examples of a mechanical pressure, mechanical sensor exploiting piezoresistive effects. So, how to measure mechanical stress? First of all, what is mechanical stress? Well, mechanical stress is any force per cross-sectional area applied to a material. So you load a material with a force and divided by the cross-section, you have a mechanical stress. And that mechanical stress is usually described by the symbol sigma in my lectures, as elsewhere also. Sometimes you find the letter S, stress S. No? And then this mechanical stress, sigma, has also some indices, yxx, yy, zz. Yeah? So what does it mean? A stress, sigma xx, is a stress that stretches a material in the x direction. So you can imagine some material which is now stressed under a force in this x direction. Let me write some x's here. And then this material has some cross section. Now I need to draw it three-dimensionally. And this cross section is A, and sigma xx is fx divided by this cross section. So if we apply such a stress to a resistor, a conductive material, exerting this mechanical stress will, visually stretch the material. That's the first idea you have. And so you know that the resistance of a material, R0, is its resistivity, specific resistance, multiplied by the length divided by the cross section. And so visually, but not really representatively, rather wrongly, you will think about this material being stretched like an elastic rubber piece and the length becoming stronger. Manuela, you saved me, thank you. You found us, wonderful. Yeah, okay. So maybe you can just hand around the scripts to the people who are here. And then okay, thank you. Okay, ja, genau. Ich denke dann dran, okay? Hoffe ich. Okay, so, danke vielmals. Bis nachher. And so this is at least the idea that the resistance will change is correct. Yeah, the mechanism by which it changes is actually by the deformation of the band structure and the minima of the conduction band, these ellipsoids being shifted in energy, and then some being more loaded with electrons than others. And because they are anisotropic, because they have different main axes, this shifts the conduction property of the electrons from more conductive to less conductive, more mobile to less mobile, or vice versa, depending on the direction of the stress. Stress can be negative, can be positive. This is called a tensile stress. In this direction, if the two arrows were pointing towards the material, it would be called a compressive stress. And so it's not unreasonable to believe that the resistance, R0, which I can write like this, this or classical formula times 1, will be changed by something. And that change, the change delta R, is usually written as R0 times pi, some kind of pi times sigma, some kind of stress. And here, in this particular case, we have pi with lots of indices, times this longitudinal stress in the x direction. Why we need so many indices will become clear in some of the next slides. Yeah. So if you imagine that this piezo-resistive coefficients, as it is called, with pi for piezo, yeah, then if this is of the order of magnitude of 10 to the minus 9 per Pascal, and the mechanical stress is of the order of 100 megapascal, 100 megapascal, then the product of those two is going to be about 0.1. Yeah. That means that to this one, 0.1 is added. Yeah. The R0 is now just taken out of the expression, and we have 1 plus pi sigma in here in the bracket. So this indicates the relative change of the resistance. Yeah. So relative change of R. Yeah. This is essentially delta R over R0. Yeah. And so it's easy to see that under a stress of 100 megapascal with a realistic piezoresistive coefficient of 10 to the minus 9, we obtain a 10% change in resistance. That's appreciable. And that also shows you that this idea of elastic deformation is not correct, because you can't under 100 megapascal stretch silicon by 10%, making L 10% longer to make the resistance 10% longer. It will move hardly a fraction of a percent, and therefore geometrically would expect a fraction of a percent of resistive change, but because of the band structure effect, you get 10%. So that's the magic about semiconductors, to have these large piezoresistive effects, much larger than metals, who only benefit of the geometrical effect. That's why silicon has become a wonderful sensor material for mechanical measurement. Now, the longitudinal stress is not the only one that can be applied to this resistor. We could imagine this material to be loaded with a stress in this direction now, Fy. Now this will make, kind of geometrically speaking, the cross-section wider and maybe the length shorter, like a rubber piece. So it is also expected to produce an effect. And yes, it does, again, through the band structure effect. The mechanical stress exerted by this force F through this cross-section A, well, let me call it Y now, as I should call A by AX here. This stress sigma YY, longitudinal stress, will produce also a contribution to the relative change of resistance via another piezoresistive coefficient, which one writes then XXYY. So now we have maybe already a systematic in the indices that starts to transpire. The first two indices that you see here, XX, this indicates something about the resistor, some knowledge about what resistive measurement we are doing. We are sending a current through the device in the X direction, and we measure a voltage drop in the same direction. X, both are X. So that's the XX in these first indices. And the other X's, the 3 and 4, indicate actually the kind of mechanical stress that we apply. Longitudinal stress in the X direction and longitudinal stress in the Y direction. Now, if there is X and Y, of course, there is also longitudinal stress in the Z direction. Let's say like this, and yet with another cross section AZ. So FZ makes some sigma mechanical ZZ, and this is translated by some piezoresistive coefficient that correspondingly must be called XXZZ. Now, these piezoresistive coefficients are tabulated, and there are 3 pieces of a tensor, a fourth order tensor that has transformational properties that is good to know. So I'll show you briefly how this goes. And the pi coefficients can be calculated, you know, they depend on the direction, yeah, of the resistor. For instance, they depend on the material. They depend on temperature, as is indicated here too. So these are material properties. And they have 4 indices. So at least we have now seen a sample of 3 of those. Yeah. But if you think that all indices could vary in principle from x to z, x, y, z, you would have 3 by 3 by 3 by 3 different piezo coefficients. 81 piezo coefficients in principle. Now, because of some symmetries, actually only 21 are really different from each other. And then because semiconductors are cubic materials, actually this boils down to 3 values that need to be remembered. And the rest is transformation laws. So we have really only 3 numbers that we need to remember at one temperature. And then wherever the resistor points to can be handled by some mathematical tricks. So this resistor here measuring this voltage drop from 4 to 1, 4 to 3, contacts between contacts 4 to 3, when current is sent from 1 to 2, is well, a 4-point contact measurement. That's how you do a voltage drop measurement. On the material, here we have some contact resistances when going from the semiconductor material to the metal. And the same here, of course. So it would be a bad idea to make the measurement out here. Although you would say, oh, this is metal, it has 0 resistance. But the contacts have non-zero resistance, and even the metal doesn't have 0 resistance. So you will slightly shift or destroy your accuracy of the measurement if you do this measurement here, because of these, I don't know how those react and how those different components react to mechanical stress. So this is a way to do it, and of course there is no current flowing through these voltage measurement contacts. They're sitting still, and you are only measuring a potential with a high resistance instrument, and therefore even if there are these contact resistances, no current flows through, and you are not disturbed by contact resistances in your measurement. Yeah, so another way to make these measurements is via Wheatstone bridges. As you know, Wheatstone bridges are quite handy. So we take 4 of those resistors in this arrangement, 2 orthogonal directions. We connect them, and then we do a measurement in between. Between contact 2 and 4. So a current will flow down here and around the corner and then out here again, and same here and out here again. And then depending on the resistance values of these 2 resistors, or these resistor pairs, the relative resistance of these resistor pairs, there will be a voltage difference appearing between contact 4 and 2. And so let's imagine a stress sigma XX. I'm leaving out the M. Why did I write M before to say mechanical? To differentiate this from the resistivity and the electrical conductivity, which is also denoted sigma. So maybe for the purpose of consistency, I will add the M here. Again, what has happened here? So, sigma M comma XX. Same here. So let's assume this MXX is applied. It will mean that this is this resistor experienced this stress in the longitudinal direction with a piezo coefficients pi x, 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 same here. And those two resistors experience a stress in the transverse direction with a piezo coefficient xx, yy. Pi xx, yy. So those two resistors of same orientation experience the same evolution under the mechanical stress, but among the two pairs, they have different evolutions because one is influenced by pi xxxx and the other one by pi xxyy. Yeah? And that creates an unbalance in the Wheatstone bridge. Yeah? So let's assume this resistor goes up, this resistor goes down, this resistor goes up, this resistor goes down. Sure enough, the potential will shift in this direction, and here it will shift in this direction, and then you have your. The nice thing about this configuration is that if you power such a device with a given voltage, with a voltage, not with a current, but with a voltage, then the fact that rho is temperature dependent is cancelled. It doesn't depend on the level of those resistors. If they all evolve in the same way under temperature in their R0 value, then this R0 change as a function of temperature doesn't play a role. What still plays a role is that maybe pi is temperature coefficient, temperature dependent. Okay, that's another story, and it's also the case. And so this remains, of course, but the strongest effect of even the resistance changes with temperature is gone. And that would be absolutely crazy, in the case of a single resistor measurement. Imagine that you have only a single resistor and you measure this voltage drop and you apply mechanical stress and you don't know about the temperature. Do you know whether the resistance change is caused by a temperature change or by mechanical stress? You know. So you're totally in the void with your thoughts, and the temperature plays a role. Here, the temperature plays a minor role. And so the main effect that makes your measurement impossible in this single resistor measurement actually is cancelled, and you can make a piezoresistive measurement. Now, I said something about contact resistances. For the same reason, this device is not a good device. Yeah. So here we have contact resistances through which a current flows. Yeah. So this would not be a good design, and that's why in my group we started, designing different sensors that had actually, green everywhere, like this. And then some contact on top through which no current flows, or even more fancy ones, just like a Hall sensor with contacts on the side. And then a current may flow in one direction through this device like this, and then you have some equipotential lines or mechanical stress is applied now to this device, and then the voltages at these current-free contacts measured, like in a magnetic field sensor. But this device is, of course, a magnetic field sensor. So here you're cross-sensitive to magnetic fields. So maybe that's not a good stress sensor. Just as a magnetic sensor, a Hall sensor of this design is not a good Hall sensor because of mechanical stress. So will this find its way out? I think it's not a wasp. It's just a little animal in search of food, or a nest. Yeah. Okay. So the better way to make this is indeed by Wheatstone bridges. There's no doubt about that. And as I showed in this applied physics letter paper, actually, Wheatstone bridges are really bad magnetic field sensors because of this cross J issue that can't develop over a reasonable surface and actually self-cancels by symmetry. And so there is hardly any magnetic response in Wheatstone bridges. And so these become optimized for measuring the mechanical stress. Now, when you look at this this device here, what will you see? Yeah, if I apply a stress in this direction, again, this is sigma xx, sigma yy, and I see that I have start dropping the m, at some point. So this will be longitudinal, this will be transversal, as I just explained, and so it should have a decent effect. And notice that here in this coordinate system, x and y designate areas, directions that coincide with 1, 1, 0 directions of the crystal. So this is a 001 wafer, the typical wafer, the CMOS wafer, and we have these 1, 1, 0 directions, not the crystalline crystal, the main crystal axis of the crystal, but these 45 degrees oriented axes. And why is that so? Because usually chips are cut from a wafer that schematically could be drawn like this with a flat. And then this machine called a stepper produces chips in many lithography steps and other technological steps, implantation and etching and so on. And those chips have their axes oriented along the flat of the wafer. And the flat of the wafer is in a 1, 1, 0 direction on these commercial wafers. And that has reason for implantation, because if you now incline the implantation machine in a certain direction, the wafer, you tilt it in one direction, and then you have best scattering of the implanted ions, and you don't get channeling and so this is parallel to the chip, and that direction is not parallel to a crystalline axis. The crystalline axis would be here. This is the 100 direction, and this is the 010 direction. So it's tilted, but we call it X. And then an analysis, which will become clearer later, I hope, is that a tabulated coefficient pi44 can be taken from the cables, can be divided by 2, and then this is the sensitivity of the sensor according to the definition which was given where. I don't see it anymore. Up here, sensitivity. It was defined before, I think. Voltage, the output voltage per stress component being measured divided by the input voltage. So this sensitivity becomes 69% per gigapascal, or 6.9% per mega, per 100 megapascal, or 0.69% per 10 megapascal, and still an appreciable number per megapascal. If this device is oriented by 45 degrees, if I expose this to this mechanical stress, sigma xx again, sigma xx, it is evident that this will not experience a piezoresistive response, because all the resistors experience the same evolution. There's a sigma xx at 45 degrees. So they're all, geometrically speaking, stretched the same way. And the band structure evolves also symmetrically, and so they will all experience the same resistance change. And so it would be an unfavorable configuration to measure the sigma xx in the sensor, because the output is always 0. However, if you imagine sigma being applied in this x prime, no, let me call this x prime, sigma x prime direction. Just remove this. In this oblique direction, coinciding with the crystal axis, 100, then it will have a response. And if I add another component like this, in this sigma y prime, so this is x prime, and this is y prime. Sorry, I should have written it here. Let's remove this hasty writing. So if I have sigma y prime, then on the one hand, the resistor, this resistor, for instance, becomes longer, again, geometrically speaking, and at the same time, its cross-section is squeezed. So geometrically speaking, we would expect the two effects to contribute to the overall response. And a combination of such stresses in this oblique direction can be described by a so-called shear stress in the original coordinate system. So an object that is squeezed in these directions, so elongated and then squeezed from the side. Let me draw this like this. Okay. But now add some additional feature. Imagine, so clearly the square becomes a rectangle, no doubt. If I inscribe another square in this original square, by joining the middle points, we still have a square. But after the deformation, we have a trapezoidal and rhombus structure. So the square was transformed into a this rhomboidal structure, and that is obtained by taking the original yellow square and exposing it to a mechanical stress like this. So on its two lateral sides, it's too small. I draw this again. So here we have this original square. And now and think of this being deep into the plane of the projection. And now I apply a force not perpendicular, but in the plane of those sides. So that was the wrong direction. Z, so here, along this direction and along this direction. What will these forces do? It will shear the structure. And if at the same time I apply this and this force, it will shear the structure as well. And if I superpose these two pairs of stresses on the side, it will create exactly this oblong trapezoidal structure. This is called shearing, and the stress, again, force per area, cross-sectional area, force applied on an area per area is called a stress, and this is denoted by sigma xy. Because the force here goes in the x direction, but the area, now I have to draw some area now at some point. The area on which this is applied, this area has its normal in the y direction. So here is where is x, y, So here, the normal vector is in the y direction, whereas the force is in the x direction. And that makes the index sigma xy here. This is consistent with the notation on this initial slide, where the area on which the force is applied has its normal vector in the same direction as the force. Both are in x direction for this yellow case here. F sigma xx. Okay, so you see that this combination of tensile and compressive stress is equivalent to a shear stress, and this sensor is able to measure a shear stress. That's what it's able to do. This sensor, of course, will also be able to measure a stress combination combining sigma xx and sigma yy in combination, better than only one of those. And in fact, it is sensitive to sigma xx minus sigma yy. So this sigma xx minus sigma yy with primed x's and primed y's, must have something to do with the sigma xy in this original coordinate system. And that is again a property of tensor transformation of second order tensor under 45 degrees, which I explained in detail in my semiconductor class in the fourth semester. So those who have attended that know that, but I know that some of you have entered here the master curriculum from outside, and so I'm at least sketching the details here. And now the coefficient that is important here are coefficients called pi11 and pi12, the difference of those. And they're also tabulated just like that p pi44. And if you take N silicon, you have a material with large pi11 minus pi12. The value that is equal to that sensitivity. If you took a p-doped resistor, then it wouldn't work. Pi11 and pi12 are small for p-doped material, and therefore you would have a very small sensitivity, a crappy sensor, for this type of measurement. So you recognize that measurement with bridge type sensors, with Wheatstone bridge type sensors with N material is best for mechanical stresses expressed as normal stresses in the original crystal coordinate system. If the Wheatstone bridge is oriented in parallel to the 110 axis, that is parallel to the flat, then it is better to take p material, because the pi44 coefficient of p silicon is high, where it is very low, very close to 0 for N silicon. So the design of piezoresistive stress sensors needs a little bit of knowledge about these pi coefficients. It's not like metal that you can place in any direction, and then these are strain gauges and they work always. No, the crystalline orientation of the silicon has its role to play. So let us just look a little bit deeper into those piezoresistive coefficients and how to transform them from one coordinate system into the other. So we have here the relationship between the electric field component and the component of the current density. The electric field is a vector. Electric field is a vector with components Ex, Ey, and Ez, and so is the current density. It's a vector with components Jx, Jy, and Jz. So, and they are related by a resistivity. Resistivity times current density makes electric field. And this resistivity actually, usually it is just given as a value ρ0. But in the case of crystalline materials under effects that break the symmetry of the material, this needs to be written as a matrix. So we have rho with two indices that run from X to Z each. And the electric field component K is obtained by summing up this matrix rho with the vector L. So you could imagine the matrix rho, I'm writing it in bold, multiply that by the vector J, and this produces the vector E. And I can also write it in bold as I usually do for vector and matrix symbols. So this is how it is done, and doing extracting EX would be just taking the first line of the row matrix and multiplying the coefficients correspondingly with the coefficients of the current density vector. And now, usually under mechanical stress or consistently with what was explained before, rho is equal to a value before the application of mechanical stress, without mechanical stress, which is a value rho 0 times an identity matrix. So this is the identity matrix written in the coefficient notation. Whenever this delta, this Kronecker delta, has indices that are identical, 1, 1, or XX, YY, ZZ, it is equal to 1. And when the indices are different, XY, XZ, YZ, or with inverted indices, then it's 0. So this delta Ki represents the matrix 1, 1, 1, 0, 0, 0, 0, 0, 0. It's called the Kronecker delta. You find that also in that. And then there is an addition that is the sum of mechanical stress components, all those stress components that might exist, that might apply to a piece of material being described by this formula. And again, the J values can vary from X to Z individually. There is XX, there's XY, there's XZ, there's YX, there's YY, YZ, and so on. So there are normal stresses and there are shear stresses. And then there are piezoresistive coefficients with indices K, L, I, J, where the latter ones are identical to the ones we find here on the stresses, and the former ones are identical to those of the resistivity matrix component we are trying to calculate under the influence of mechanical stress. So how does one transform the resistivity from one coordinate system to another? So if coefficients pi11 and pi22 are given in this coordinate system, X and Y, because they are tabulated like that, and because that's the natural way to do it, can we calculate them in another coordinate system that is rotated by 45 degrees? So it seems that pi11 and pi22 have something to do with the translation of normal stresses in that coordinate system in which those coefficients are naturally defined. And so what about a sensor that is rotated by 45 degrees? Now the describing coordinate system is rotated by 45 degrees. And so which coefficient should we apply? Can I calculate those? And so this question is obtained by some transformation rules, where a matrix M plays an eminent role. It is called the transformation matrix for the coordinate transform from coordinate X, Y, Z into the coordinate X, X prime, Y prime, and Z prime. And this matrix is again a 3 by 3 matrix. And to calculate rho in a new coordinate system, you need that information about this M. I'll have to describe how this is obtained. You'll have to fudge it up somehow with the resistivity in the original coordinate system, and then you can calculate all the components in the transformed coordinate system. So this is for rho, the same is true for sigma, the mechanical stress. Yeah, and you see that the formula is identical because the stress matrix with its two 3x3 indices, yeah, is a two-dimensional matrix. It's a rank 2 tensor, just as rho is a rank 2 tensor, and tensors of the same rank transform identically under coordinate transforms. Yeah? And the fact that these two tensors have two indices, they're of rank 2, means that M needs to be implemented twice in this formula. For pi, the situation is analogous. Yeah? Pi coefficients can be calculated in arbitrary coordinate systems, given the values in an original coordinate system, given the rotation matrix that maps one coordinate system or the other. But because we have 4 indices, we need 4 such M expressions with indices corresponding. Always the first one is found here on the left. K prime, L prime, M prime, N prime. The first indices are found here. And the second indices K, L, M, N are found here on the right. Yeah? So this is a calculation rule that can be mechanically applied, actually. You know, if you feel uncomfortable with those rules, then my recommendation is just apply them, and then you will see what comes out. Yeah? Now, this transformation matrix, yeah, what is it? Yeah, so I'll draw a coordinate system here, for a simple case. Yeah, so we have an x-axis, a y-axis, and a z-axis here. Yeah, and I'm drawing Ex, a unit vector in these two directions. Yeah, and then of course out here we have an coordinate vector Ez. Now let's assume we go from this original coordinate system x, y, z to a rotated coordinate system. I'll write it in blue. Yeah, so we have this direction. Yeah, we have a new Ex prime. Well, this is kind of the x prime direction, and this is the y prime direction, and I'm writing here coordinate vector, no, unit vector Ey prime. And then because the rotation was done here by an angle theta, of course, Ez prime is the same as the original Ez. So this is one very particular case of a coordinate transform. Yeah? For this particular coordinate transform, the matrix M takes the form M equals cosine theta sine theta 0 minus sine theta cosine theta 0 0 0 1. Huh? And actually, that's the only case which we will have to use in this vector, because we're always in these 1, 1, 0 wafers. And we always think about centers being rotated in this or that direction on the surface of that wafer. So the z-axis always remains fixed. If you once in your life, you will encounter a 1, 1, 0 wafer or a 1, 1, 1 wafer, bipolar technology wafer, then you need to think more profoundly, and then the matrix M may take a more complicated shape. But by that time, you'll find all this very easy, hopefully. So now, what does this express actually? You know, you can imagine, this Ex prime vector. What components does it have in the original coordinate system? It has the components cosine and sine, doesn't it? The x component of Ex prime in the original coordinate system is this length here, this segment. That's cosine of theta, and this segment here is sine of theta. So these coefficients essentially express the value of the new coordinate direction vectors in the old system. Yeah? So that's how the transformation is described. And these, this matrix with its coefficients M11, M12, M13, M21, M22, 23, and so on, is the one that is implemented in these formulas. Yeah? And so you only have to write these incredible sums of products of numbers, most of which are zero anyway. And then what remains to show you what the pi coefficient in the new coordinate system will be, or what the resistivity or what the mechanical stress in the new coordinate system will be. And this is how you show that actually a combination of normal stresses like this is equivalent to a shear stress in another, in a 45-degree rotated coordinate system. So applying this formula for sigma leads naturally to this connection, that this unprimed sigma shear is equal to a difference of sigma normals in the x and y direction. And so this, if we look at this stress here, this must be a shear stress in the rotated coordinate system. And yes, it is the case. It is as shearing, pulling it along and squeezing it from the top is the same as shearing it in a coordinate system that is under 45 degrees, and then you obtain the same effect. All right. So these coefficients are well known. Actually, it's wonderful in silicon because of the cubic symmetry structure of silicon. Pi xx, y, so with 4 indices, y, x, y, and z, they're all the same. And x, y, and z actually here, well, actually, no, it is called pi L, longitudinal. So my mic was already ahead of what I wanted to say. So this is a longitudinal thing because it describes the effect of stress that points in the same direction as a resistor when the resistance of that resistor is being measured by a current in the same direction and the voltage difference in the same direction. So that L for longitudinal makes absolutely sense. These indices with pairwise unequal values are called pi transversal because the normal stress acts perpendicularly to the measurement of the resistance. So transverse also makes a lot of sense. Here you have M again expressed as let's say Mathematica would express, or how we would implement it in Mathematica. It's this 3x3 matrix that I just drew before. And these pi coefficients are known since the 50s of the last century. For silicon, at least, they're given by pi longitudinal equals pi 1, this value. And the mixed coefficients are expressed as pi 1, 2. So this is a transverse coefficient with this value. But because they transform under a coordinate transform, we need to know for what coordinate system. And the coordinate system that it applies here is that of the cubic crystal axis. So people who measured these coefficients said, okay, the natural coordinate system is the crystal coordinates. I measure my sigma xx by measuring a resistor along that crystal coordinate under a longitudinal stress, and I call that coefficient pi xx because that's my x direction. And I will shorten this clumsy nomenclature by calling it pi 1, and it has the value of -102, and pi 1, 2 has the value of 53. And then the shear stress piezo coefficient, those with mixed indices otherwise, those that will cause other effects, those are called shear piezo resistance coefficients. And again, many of those are equal Yeah, you can switch coordinates. You can switch only one pair or the other, and so on. So there are 12 of those, and they all have the same value, and it is called pi 4 actually. Those coefficients are pi 4 divided by 2. That's the definition of pi 4 for historic reasons. And it has a value that is comparatively low with the pi 1 and pi 12 values. That's for N doping. For P doping, the situation is different. Here, the longitudinal coordinate, longitudinal piezo coefficient along the cubic crystal axis is small. Yeah, minus 100 here is only 6. Pi 12 is even smaller, only 1 instead of 53. But to compensate for that, the shear piezo resistance coefficients are pi 4, expressed as pi 4 are rather large. And etc. here means always that you can just replace the indices by cyclic permutation from replacing x by y, y by z, and then you get other combinations that are also equal. And those are the only coefficients that are different from 0. So from the 81 coefficients, yeah, you have 3 that are equal to one number, 6 more that are equal to another number, and here we have 12 that are equal to a third number. That makes 21 coefficients that can in principle be different from 0, and they are only equal to 3 different numbers. So there's not so much to remember, except for the fact that which ones are equal. So when we apply these transformation laws, this is a graphic that I took from my semiconductor lecture. We see that pi longitudinal is orientation dependent, and therefore designing a sensor requires a bit of thinking. So what we see here is the number of minus 100. It's written here minus 100. Well, it depends, which curve this refers to. So the top curve or the bottom curve. So let's consider this pi longitudinal. This direction is a 100, is the 100 direction. This direction is the 010 direction. What this says is that if you have a sensor that is sensitive only to the pi L, or is exposed to a situation where only pi L plays a role, then it will be responsive with minus 102 times, of course, the 10 to the minus, plus 100 gigapascal per gigapascal. So 10 to the 100 times 10 to the 9 Pascal, or 100 gigapascal. So what was it here? So it says 100, oh, damn it, 100 times 10 to the minus 11. Yeah, that's correct, because this determines the size of this exponent. So this corresponds to minus 1.02 per giga. I shouldn't have written the Pascal here. I'm sorry, I apologize. Let me erase this again. That was too hasty. So always these numbers should be thought to be multiplied by 10 to the minus 11 per Pascal. So and it means that a resistor oriented along this 100 axis is going to be quite sensitive to mechanical stress. If you take a resistor that is oriented in a 110 direction, so this would be a 110 direction, and this here would be a a 1 minus O direction, so 45 degrees. This is only 30% of sensitive, so it's not a good idea. In contrast, P silicon has hardly any response for a sensor of this orientation. Yeah? However, a sensor oriented in this direction has a strong response. Yeah? That's the result of the transformation of this strong pi4 coefficient into the 45-degree direction, which now becomes suddenly very large, whereas here the value is, what is it, 6.6 times 10 to the minus 11. Yeah, nothing to seriously speak about, but under 45 degrees, yeah, this makes sense. Yeah, it makes much more sense than to use an N resistor. And so these are values for the longitudinal effects, which are seen to be complementary, where P is bad, N is good, and where N is bad, P is good. Yeah, and the same is true for the transverse effect. Also, the transverse effect is relatively strong with positive values in the cubic crystal directions with 53. That's what this coefficient pi12 says, 53 plus 53. And then at angles around 45 degrees, the response is rather weak. It's even a bit negative. It goes to 0. It's not very significant. Whereas the pi transverse coefficient, well, that has a decent value again, because of pi4 transforming into this large value under 45 degrees. And then, well, this I could just put between brackets. It's not of relevance here. And so, what are those coefficients? Here you see some values, and that's going to be the last slide of today's lecture. Measured values that we have measured with integrated piezoresistors diffused in commercial silicon. I think this was produced by X-FAB in a project, and you see N-well resistors in a P substrate with some nominal doping. You see P diffused resistors here in an N-well, and another N-well in a P substrate rotated under 45 degrees. The one is certainly, so this must be a 110. This is the 110 direction. Yeah. So this is to measure the shear coefficient of N material. This is to measure the longitudinal and transverse effect of N silicon, and this is to measure the pi11, pi12 coefficient of P silicon. And you see here some values tabulated as a function of temperature measured by Pascal Gischke, PhD student of mine, on these substrates. And well, the values correspond pretty much to what one expects. Yeah, so 102. Here something like minus 13. Here something around 53, and then they all decrease with temperature. Yeah. This value here is maybe smaller than 136. This P doped should be 138 for pi4. It's definitely not that value. Yeah. But the coefficients that were mentioned here are actually for low doped P silicon. And this material may not be so low doped. And it is also known that the doping level decreases the piezo resistance coefficient, making the piezoresistor flat again. So I think I will stop here. Yeah, that's a good moment. And then I'll explain some other things about piezo FETs, and then about how to measure those pi coefficients with experimental infrastructure, and then how to apply those sensors in systems. Yeah? There is one thing that I wanted to say before closing. I will upload some exercises again regarding the material we have covered now. There has been some time spent since the last sheet of exercise was defined, and so this is to be worked on until next week. If you say Tuesday is better for you, we'll do it on Tuesday, then you can participate also in the exercise. Or what do you prefer? You don't come. Hey, I wouldn't be here without you. Yeah, you count essentially. Yeah, okay. No, please speak up. You know, you can speak free. Yeah, if you say I'll do it for fun anyway. Lecturing is more fun than exercises, and we'll do it on Monday, and then we'll do again lecturing on Tuesday. Yeah. Any other opinions? I just gave an argument. Yeah. For those who come for fun, for those who must, maybe you have other reasons, other objectives, or other reasons, non-emotional reasons. Yeah. No preference. Then let's do it on Tuesday. Yeah. Okay. Yes, I'll just stop here, stop sharing, and then first I have to stop recording. Where is that? I don't know how to stop recording now. Ah, here it is.